Hello learners, I am Dr. Subodh Kishorwani, working with Indira Gandhi National Open University in School of Management Studies. The topic which I am going to talk today is related to the course called MCO3 Research Methodology and Statistical Analysis. We are in block 4 which more focused on testing, and we have very elaborately talk about the estimation in our preceding session. Now we are moving towards one step ahead and now more focusing on the confidence limits, confidence intervals and confidence coefficient. I think when we talk about confidence, this is a very important aspect because this confidence level is going to provide you a platform, a researcher a platform to know more about and interpret the estimate for a single population proportion. So construct and interpret a confidence interval estimate for a single population mean using both the Z and T distributions. Form and interpret a confidence interval estimate for a single population proportion. Form and interpret a confidence interval estimate for a single population variance. This we are going to cover in this coming sessions. And if you go into the backdrop, you will find out that confidence, there is a great difference between the confidence interval and confidence level, which we are going to take in a very strategic manner under the ambit of comparison. And if you talk more about a confidence interval displays the probability that a parameter will fall between a pair of values around the mean. Confidence intervals measures the degree of uncertainty or certainty in a sampling method. They are most often constructed using confidence level of 95% or 99%. So if you see this particular image, you will find out that a 95% confidence interval indicates that 19 out of 20 samples, which comes to 95% from the same population, will produce confidence intervals that contain the population parameter. So in statistics, a confidence interval is a type of estimate computed from the statistics of the observed data. This proposes a range of plausible values for an unknown parameter, for example the mean. The interval has an associated confidence level that the true parameter is in the proposed range. The level of confidence can be chosen by the investigator with high degree of confidence, requiring a wider, less precise confidence intervals. In general terms, a confidence interval for an unknown parameter is based on sampling the distribution of a corresponding estimator. So, changing the confidence level to create a 99% confidence level, we must also widen our 95% interval. On the other hand, if we want an interval with lower confidence such as 90%, we could make our original 95% interval slightly slimmer. So you see that if you see this particular image, you will find out 99% extent from minus 2.58 to plus 2.58 and 95% extent from minus 1.96 to 1.96. So this is the way by which we are going to see the confidence level of any sample which we have taken. So the confidence level represents the frequency, that is the proportion of confidence intervals that contain the true value of the unknown population parameter across many independent experiments. In other words, if the chosen confidence level is 90%, then in a hypothetical scenario where an extremely large number of independent experiments were conducted, then as the number of experiments increases, the proportion of the confidence intervals that contains the true population parameter will tend towards 90%. So there is a good number of difference between the confidence interval and confidence level. If you talk, a confidence interval is a range of values that likely would contain an unknown population parameter, whereas if you talk more about the confidence level refers to the percentage of probability or certainty that the confidence interval would contain the true population parameter when you draw a random sample many times. So it is the probability that the population parameter value lies between a specified range. And if you talk about the confidence level, it is used to statistically state the range of an estimated / predicted value. So confidence intervals are your results and they are usually numbers. Confidence levels are usually expressed as a percentage, for example a 95% confidence level or 99% confidence level or 92% confidence level. This could be one of the way of interpreting the confidence level. So here when we survey a group of people using sanitizers to see how many bottles on an average are sold in a year, it will be a range of numbers, for example 200 to 250. And when we talk about confidence level, here we repeat an experiment or survey again and again. 95% of the time your results will match the results you get from the populations. So we have seen that as far as the interval estimate is concerned, this is another type of estimation, and in statistics, interval estimation is the use of sample data to calculate an interval of possible values of an unknown population parameter. This is a contrast to point estimation, which gives a single value. So Jerzy Neyman identified interval estimation as distinct from point estimation, as opposed to estimating a parameter by a single value, that is point estimation discussed in the previous section. We may think of an interval or a range of values that is supposed to contain the parameter. An interval estimate would always be specified by two values, that is the lower value and the upper value, within which the parameter lies. So this is known as interval estimation. Thus, interval estimation may be defined as estimating an interval to which the known parameter theta may belong, which is expression of the term in all likelihood. So if you see the confidence interval estimates, we have two black dots and one red dots in between, and interval is this only, where and point estimate is minus reliability factor, and it is multiplied by the standard error, and then point estimate plus reliability factor multiplied by standard error. So if you see the formula, this is x bar minus reliability factor multiplied by sigma upon square root of n, and then if we express this particular formula, x bar plus reliability factor multiplied by sigma upon square root of n. So this is the formula. So if you see this image, I think this figure is quite self-explanatory, that if we talk about the bell-shaped curve, which is purely a bell-shaped curve, and if you see the confidence interval, I think 68% of data, if we are talking about, this is called 68% confidence interval, and if we talk about 95% of data, which is coming 95% confidence interval, and if we talk about 99.7% of data, which is considered as 99% confidence interval. So this is the way by which we are going to interpret. And if we go more into the depth of interval estimates, which is also called a confidence interval, a range of numbers that we think has a given probability of containing a parameter. The probability that interval estimates contains the parameter, typically confidence coefficients are 0.95 and 0.99. We usually are told the desired confidence coefficient, then asked to find the interval estimate appropriate for the confidence coefficient. So example of confidence interval is 95% confidence interval for a sample mean. 95% of this confidence interval equals to y bar plus minus 1.96 multiplied by standard error, which is expressed by y, and 95% of this interval equals to y bar plus minus 1.96 multiplied by sigma y. So example using age from IHDS, if we talk about the summarized age is 215754, mean is this, and if we calculate it, I think this could be the way by which we are going to calculate. So equation for interval estimate is confidence interval for mean is y bar plus minus z sigma y bar and proportion. So confidence interval of pi is plus z pi sigma pi, where sigma y equals to s oblique square root of n, and where you choose z based on the p value for the confidence interval you want, and there are certain assumptions. The sample size is large enough that the sample distribution is approximately normal. So usually we are not given z, instead we start with a desired confidence interval, that is 95% confidence, and we select an appropriate z score. We generally use a two-tailed distribution in which half of the confidence interval is on each side of the sample mean. And what does this do to our choice of p values for the z score? So equation for interval estimate is like when we talk about the example, that is finding the confidence interval when y bar is equal to 10.2, s is equal to 10.1, n is equal to 1055, interval is 95%. So z is derived from the 95% value. What value of z leaves 95% in the middle and 2.5% on each end of a distribution? So p equals to 0.975 and z equals to 1.96. The standard error is square root of n equals to 10.1 and square root of 1055, which comes to 0.31095, and top of the confidence interval is 10.2 plus 1.96 multiplied by 0.31095 equals to 10.8095. So the bottom of the interval is 10.2 subtracted by 1.96, which is multiplied by 0.31095 and equals to 9.5905. Hence the confidence interval is 9.59 to 10.81. So normally rules for confidence, normality rule for confidence. So if we talk more about the normality rule for confidence, confidence interval assume a normal distribution of possible sample. When can you assume normality for a sampling distribution of a continuous interval variable such as income? When n is greater than or equal to 30, when observation in the population can be assumed to be normally distributed. So confidence limits or intervals are commonly used in association with statistical calculations. Available data are normally considered to be a sample that is used to estimate characteristics of the overall population. The population is all possible data including possible future measurements. The sample data can be used to calculate a point estimate such as an average leak rate in leaks per mile per year. A point estimate approximates the value for the entire population of data termed the true value. However, the approximation is affected by the uncertainty in the sample data set. A confidence interval bounds the uncertainty associated with the point estimate. For example, a leak rate estimated to a 95% confidence level has a 95% probability of including the true leak rate. So now the time had come where we can find a critical value of Z. So Z is equal to plus minus 1.96 while considering a 95% confidence level. 1 minus alpha equals to 0.95 and alpha by 2 equals to 0.25. If we see, this is the way of doing it, and alpha divided by 2 here is 0.25. So in both cases we have seen that alpha by 2 is 0.25 and Z is since we are here, so Z is equals to minus 1.6, and since we are after the 0, after the x-axis 0.0, then Z is equal to 1.96. So this is lower confidence limit which is negatively quoted, and point estimate is 0, and upper confidence level is positive 1.96. So now we are going to talk more about the common level of confidence, which is commonly used confidence levels are 90%, 95% and 90%. So we have a table in the first column which talks about the confidence level. The second column talks about the confidence coefficient, which is quoted by 1 minus alpha, and then we have a Z value. So if the confidence level is 80%, confidence coefficient comes to 0.8 and Z value comes to 1.28. If the confidence level is 90%, confidence coefficient is 0.9, Z value comes to 1.645. If the confidence level is 95%, confidence coefficient comes to 0.95 and Z value comes to 1.96. So in the same manner, if we go through this particular table, we find out that if the confidence level is 99.9%, confidence coefficient is 0.99. So and Z value is 3.27. So this is one of the way of talking more about or pictorial presentation of common confidence intervals. If the confidence is 95%, alpha is 5%, this is the way of interpreting the figure. If the confidence is 95%, alpha is 5%, this is the way of interpreting the figure. So confidence is 95%, alpha is 5%. So this is another way of, so you will find out critically value is minus 1.65 and the critical value is 1.65. So if the confidence level is 95%, critical Z critical value is minus 2.33, and if you see this confidence level is Z critical is 0.2.33. So this is the way when the number of data points available is small, the confidence limits are wide, indicating that not enough information is available to be confident that all future data will be close to the small data set already obtained. Data on pipeline failure rates are limited. The use of upper limits of statistical confidence intervals, especially a high 95% confidence level, would not present meaningful representation of true failure potential. It will present unrealistically large predictions strictly as a result of the small number of data points available. So confidence interval for population proportion is quoted by pi plus minus z, where pi could be in square roots. In brackets we have 1 minus pi divided by n. So if we take example of 424 of 1000 respondents in a poll rate that they plan to vote for a candidate X, calculate a 95% interval for this result. So confidence interval for this result is 0.424 plus minus 1.96 and multiplied by square root of 0.424 into 1 minus 424 divided by 1000. So if we calculate, we get a figure 0.395, which is greater than or equal to 4.455. So normality rules for confidence interval for sample proportion is: when can you assume normality for a sample of a dichotomous interval variable? Yes is equal to 1, no is equal to 0. When n is in brackets, probability of 1 minus p greater than equal to 10. So for what values p do you need an extra large n to ensure a normal sampling distribution? What can go wrong when you appropriately assume a normal sampling distribution? So putting it all together, given the following samples of 7 observations, 5, 2, 5, 2, 4, 5, 5, what is the 95% confidence interval of the population mean, and what is the best phrasing for an interval estimate? So the 95% confidence interval for the population mean is 6.8 to 9.5, and there is a 95% probability that the true population mean is between 6.8 and 9.5. We estimate that 95% of sample from the underlying population would fall within 1.35 of the true population mean, and we estimate that the true population mean is 8.15. So if you see this particular chart, confidence interval for mean and proportion using this confidence interval is 95%, confidence interval for general social survey, and if we go into the backdrop, we find out that variant with higher threshold for confidence is coming 99% and 95% confidence interval for proportion as per the A and F example. So now how to choose the best sample size? So cost is directly proportional to sample size, and so if your sample size is more cost is going to be involved. So we generally want the minimum sample to do the job. Estimating minimum sample size is commonly done with population proportions. With population proportion, you do not need to make separate guesses about the population mean and standard deviation. With population proportion, it is easy to identify a conservative mean and the bias does not vary much. Choosing the best sample for a population proportion, we already have an equation for the confidence interval, which is quoted by pi plus minus z. In brackets, we have pi 1 minus pi upon square root of n. So when we choose the best sample, we choose one half of the confidence interval, the top one, and solve for n. So n equals to z square and then multiplied by pi 1 minus pi upon this intervals, top 1 by 2 minus pi square. So accuracy in Finlay term for one half of the confidence interval is the confidence bound B. So sample size for election poll, if you talk about desired 95% interval, is equal to plus or minus 3%. So preliminary estimate is pi is equal to 0.25. What could be the sample size? So choosing the best sample size for a sample mean, estimating minimum sample size is less commonly done with population means. With population means, you need to make separate guesses about the population mean and standard deviation. We generally have a hard time making a good guess about a population standard deviation without measuring it. So choosing the best sample size for a population mean, if we talk about, this could be the way. So anyway, I think we have talked a lot about this intervals and the estimation in a more elaborative manner. Now we are moving towards the hypothesis testing, and in coming days you will find out that more session is going to come which more focus on the testing and emphasize how to execute the whole process. Either it could be the two-tailed or one-tailed test, or the ANOVA or t-test, which can come under the ambit of the testing of the hypothesis. Thank you very much. We have some more thought-provoking sessions in coming days. Thank you.